Hello, I'm Rajaratnam. I previously taken data X course in my graduate program at UC Berkeley. With that, let's get started with today's module. Today we're going to look at part 2 of convolutional neural networks. And in this part 2, we're going to build a baseline cats versus dogs image classifier and then use data augmentation to improve the accuracy a bit. And then we're going to see how to use transfer learning to leverage pre-trained networks in order to build a powerful and an accurate image classifier. And finally, we're going to visualize CNN learning. So let's get started. First, we're going to build a baseline cats versus dogs image classifier. As usual, we need the data and some of the basic libraries. And we're just loading the folders, looking at the number of images available for training. So we have, for each category, we have 1000 cat images, 1000 dog images for training, and 400 cat and 400 dog images for validation, and 100 unlabeled test images. And let's assign some of the constants, and let's fix some of the variables. And we need to pre-process the data. We need to scale it and convert into floating point tensors. So we utilize keras dot preprocessing.image, and we get image data generator to start the process. Here we're converted into patches, and next we're going to build a model. It's a simple model, sequential model with um, convolution layer, subsampling using max pooling, again convolution, max pooling, convolution, max pooling, and we use a flatten and then two dense layers. The last one is an output layer. Since it's a binary classification, we just have one output, and it's a sigmoid activation. Let's look at the summary. Here we have the summary of the layers, the output of each layers, the shape, and let's compile, providing the loss, the optimizer with the learning rate, and the metric. Now let's train it. Now this will take a bit of time. Now we see that the training is complete, 30 epochs, and once we finish that, this is the code to save the model so that a trained model can again be restored and then maybe further trained, or it can be used to test or predict on unlabeled data. So let's save it, and this is how we would load it. And let's look at the summary. We'll test it on validation data. We see that it's around 70%. So let's plot it. There we have. So this is a classic case of overfitting where the training is very close to 90, whereas validation is around 70. So this overfitting can be reduced by using dropout and regularization. Also, we're going to utilize a specific method in computer vision called data augmentation, where we're going to add noise, add distortions to images to generalize the model for unseen data. So next step is we're going to do data augmentation, and we're going to add rotation, we're going to add shift, we'll provide the range, zoom, shear, horizontal flip, and create a new data set from the previous one. This is a way in which we can visualize how the data looks like. So this example, so you see, after applying augmentation, there's a flip, there's a rotation. So this is how the image is transformed. Now let us create the validation and the training data generator, and we're going to do the same thing, the model, and then we're going to compile it. Now let's train it again. This could take a bit of time. So now the training is completed, and after 50 epochs, let's save the model and load it. Let's check on validation data. Good, we have an accuracy of around 78, an improvement, and then let's plot it. So this is pretty good. Next, let's look at visualizing the results. So this is how what our model thinks that picture is, what each picture is. So far so good. Yeah. In transfer learning, we are going to utilize a pre-trained CNN for our dataset of interest. So this reduces the effort to train a new neural network from the scratch. What we can do is we can uh, take a pre-trained CNN with its weights provided. We can modify it and just train the parts or the layers that we have modified, keeping others frozen or untouched. This reduces the effort to train an accurate uh, CNN for image classification and reduces resources required for the same. So in this case, what we're trying to do is we're going to use VGG16, which was trained on ImageNet. You know, ImageNet is a dataset consisting of thousands of classes, and we need only a classifier that can classify just two classes, cats or dogs. So the idea here is that since it was trained on thousands of classes, the low level features are detected well by the initial layers of the CNN. Only the final few layers or the dense layers have to be removed and then swapped with the new output size, which is 1 for this case since it's a binary, and then retrained, which will be much faster. So for that, we are going to extract the features. So this is the look of the VGG16. So we are going to remove this last block and then swap it with our custom fully connected classifier for the number of classes that we want to classify, keeping all these same. And to ease up the computation in this case and to reduce the load on the CPU, what we're going to do is we're going to record the features at the end of this block, that is the output of the last block, and save it in a numpy format, and then uh, train the last layer by feeding, instead of an image, we'll just feed the features that are an output of this model. So that is what we mean by extracting bottleneck features. So this is another visualization, and this is the code of how the VGG16 can be built. And this VGG16 in 2014, it had the second place uh, for the ImageNet challenge. So it's state of the art. It was one of the state of the art methods. Now, with this function, we are trying to save the bottleneck features. So, yeah, bottleneck features are saved. Now, just a bit of preparation, and then we're going to create the last few layers and add our number of classes that we want. Since it's a binary classification, one is enough. And we're going to compile it, and we're going to save the best weight uh, out of 20 epochs. And we are not only going to save the best weight, but also we are going to save it in a JSON format, the model architecture, so that it can be uh, built or sorry, restored again. Now see, the training is very fast because it's just training the last few uh, fully connected layers. Now let's load the best weights, and this is how the new layer architecture looks like. Only the last few layers in the input. Instead of image, we're going to feed the features. This is the graph. So let's test it on validation dataset, and next we'll be testing AC. This is 90 compared to the previous 70 and 74, around 74. Now let's look at some output. So this is how the model thinks, with 0.99928 probability that this is a cat. And the same goes for the next few pictures. Here it makes a mistake, but it's 0.5 is the probability, so it's not so sure. There you go. Now the final part is, let's see how uh, the learned layer looks like. For this case, what we're going to use is the second CNN that we built using data augmentation. So we're going to reload this model and pass one uh, image, cat image, and visualize how each layer filters the features. So this is the cat image, and yeah, this is how one layer looks like. But how about visualizing all the 8 layers and the multiple filters associated with them? It'll be fun. There you go. This is how it looks. So if we could see here, so these are the initial layers that utilize the low level features. There's no full outline form, but these are combined throughout, and in the later layers you could see the overall outline, and in the last few layers you could see a complete picture of a cat being formed. This is how these are the result of training a CNN. And that's all for part 2.